In the final section of this chapter, we consider adapting the Newton-Raphson method to the solution of n simultaneous nonlinear equations. So what we've indicated here is a vector-based representation of a system of nonlinear equations, as illustrated here. And what you have is a representation of a series of functions f sub 1, f sub 2 through f sub n of three independent parameters x1, x2 through xn. But the idea here is that the f1, these f sub i's, are nonlinear in the sense that they involve powers of these xi's that are not just one. It could be square roots, it could be exponentials, it could be x squared, x cubed, and so forth. So trigonometric functions, whatever, but they're definitely not linear. So this is not using LU decomposition or Gaussian elimination to solve them. So it turns out you can extend the Newton-Raphson method that we've been using to find roots to solve for the solution vector to this system, which is indicated right here as, again, finding the x1 through xn's that simultaneously solve or satisfy all n of those nonlinear equations. So in the case of a system of nonlinear equations, what we'll look at is the Taylor series expansion of each one of those f sub i's applied to the vector x, which remember has n components, x1, x2 through xn. And what you see here on this slide is what that Taylor series expansion looks like for a multi-parameter function f. So f of I here, the f sub I is a function of n parameters, not just one. So it's multidimensional. So what we're representing is movement in the Rn space. So we're living in this case in Rn, and this shows you how you can advance through the space by taking the vector x position and then adjusting it by a delta x vector position. And what's complicated here is that because f is a function of many variables, rather than a single derivative, you have to evaluate partial derivatives of f sub I at all of the different variables you have x1 through xn, and multiply that by this shift in Rn space, plus an order delta x squared term, very similar to what we had in the one-dimensional case. So if we were to drop this last term in terms of, developing an approximation of how we would move in the Rn space, then what we would have, is indicated down here at the bottom, is actually a matrix vector representation of an update of f sub I of x. So that if you want to move in Rn space from this vector position x to the x plus delta x, again those being vectors, what you would have to do is move from the current position by this shifted vector here, which is represented as a matrix times that increment vector delta x. And that matrix has a special name. It's an n by n Jacobian matrix. And the Jacobian matrix is formed by evaluating function f sub I at, with respect to the jth independent variable x. So as indicated here, the ij component of the Jacobian is whatever row that specifies. It'll be the ith function f sub I, the derivative with respect to the partial derivative of that with respect to xj. Okay. Again, what does that mean in terms of partial derivatives? Is looking at everything being held constant except for the variable xj, taking the derivative with respect to x of j. So just like we had in the one-dimensional case, if we assumed that we were at the solution of that nonlinear system such that it was the solution to the vector value, all the functions being set to 0, then we would let x plus delta x be our improved approximation. And then the question would be, well, if that's true, then how do you determine how much to move from the current position x to x plus delta x? Well, if you move in a way that it satisfies the equations, in other words, equal to 0, then we would have this particular case. And then if you go back to the iteration description we had just earlier, if that is equal to 0, then that would mean this left-hand side term would be equal to 0, and then you could just readjust this equation here by taking the f sub I term to the other side, and now what you've got is a linear system of equations. Again, because we don't know what the delta x is, we do know where we currently are in the space, and of course we would negate that. And the Jacobian matrix is determined by those partial derivatives. So what's interesting here is to solve the system of nonlinear equations essentially results to solving a linear equation. So many times what people would say is that a Newton method, in this case Newton-Raphson for solving a system of in nonlinear equations, is a linearization. It's actually linearizing the problem so that you can solve a linear system, essentially to advance the solution of a nonlinear system. So here's the method. Again, it's an iterative method in the sense that you would have to have an estimate in Rn space. Again, you're living in Rn, so you're trying to solve for vectors. You're trying to get in components x1 through xn that satisfy all of those nonlinear equations set equal to 0. And so you'd have to take an estimate, then you'd have to evaluate your system at that point, then you would compute the Jacobian, then you would solve the Jacobian for the step in Rn space, then you would take the step in 5 right here, and repeat this until, like we had before, that your increment is essentially too small to see any significant change. In this case, because we're living in Rn space, we'll evaluate the 2 norm of that increment vector. Do keep in mind this is a vector. Okay, so this is a vector of all the adjustments you're making in all n dimensions. They may be very different or very similar, doesn't matter. But when that change is relatively small with respect to the 2 norm, you've essentially converged to something which we hope is the solution to the nonlinear system of equations. So if someone asks what's the complexity of using this nonlinear, this Newton-Raphson method for solving nonlinear systems of equations, it would result to the complexity of solving the Jacobian matrix. And you'll remember that in the iteration, you solve it every iteration. I will point out that in the literature, you would see sometimes what's called a quasi-Newton method. You may see this word before the Newton method. And the quasi-Newton methods are attempts to avoid having to solve that Jacobian system every step, ways of maybe exploiting some other properties of the problem so that you can avoid having to solve a linear system every step. But that's more of an advanced topic for this course, but just something I wanted you to be aware of. The reality, though, is if that partial derivative of f sub I with respect to xj is difficult to compute or impractical to compute because the f sub I is a very complicated nonlinear function. You could have signs of exponentials under roots and things like that. One way you can approximate that partial derivative is by this particular ratio here, where you could estimate that partial derivative by just 2 function evaluations of f psi divided by what we call a step size h. And this ej vector is just a vector of all zeros except for a 1 in the jth component. This is actually going to be a topic of discussion in the next chapter. This is a way of approximating derivatives, and so we will do approximation of derivatives in chapter 5. But for now, it's just important to know that there are ways that we could approximate the Jacobian without having to do a very complex computation, perhaps, to construct that coefficient matrix for each step. So I will provide the Newton-Raphson 2.py script file, which actually is an implementation of Newton-Raphson for solving a system of nonlinear equations, as well as an example 4.5 code on pages 165 and 166. So both of those are on Blackboard for you to be able to download and play with. And I'm going to go over them in just a second so you'll get a better understanding of how the method is implemented in Python and then I'll run that example 4.9 for you, and then briefly go over two interesting applications of Newton-Raphson, which will be somewhat related to homework that you're going to be able to do. And they're problem 16 and 26 on pages 167 and then 170 and 171. One is from structural mechanics, and the other one is actually from graphics in terms of constraints on circle drawing. So here is the code for Newton-Raphson. It's called Newton-Raphson 2. This is on page 163 out of your textbook. And just going over from the doc string, you can see that it's going to need a passive function by name called f that would have to be able to return an evaluation of the system. Remember, this f now is multifunctional. It has f1 through fn given an initial vector. So this is not a scalar value here. This is a vector x. And then again, we will use this user supply tolerance, the default value of 10 to the minus 9, to be the tolerance on the 2 norm of the increment vector delta x. So when it becomes less than or equal to that value, the iteration would stop. So just looking a little bit at the definition of this function. Whoops, let's go back. Let's get back to 163 here. I'll go back to my bookmark. What we've got here is defining initially the Jacobian function. So it's a function that would provide the value of the Jacobian at the vector x. So again, now this is the technique of actually approximating the Jacobian value, the partial derivative of fi at xj, using a step size here of 10 to the minus 4, a very quick step of approximating the derivative. Again, we'll talk about this approach in the next chapter, but this is a way of approximating the Jacobian with just two functional values, rather than having to actually compute a derivative. So again, this will work very nicely if computing the derivative, or the partial derivative I should say, is a very complicated, messy formula that could be taking up more computation time. So the Jacobian is approximated in this step by this function, so that the method is simply stated right here for I in the range of 30. So we will go 30 iterations. If it doesn't converge, this message would be printed that it's going to require too many iterations for the method to converge. Mainly, that means you need a better starting guess. Keep in mind, just like for one-dimensional problems, even when you're solving a system of nonlinear equations, where you start this method matters in terms of how fast it's going to quadratically converge. And so you need to immediately compute the Jacobian matrix. You take your starting value for the Jacobian matrix, and this is just testing for the delta x increment, because you will solve that system for the increment, and then the increment, I guess I should point out, is right here. Remember your Gauss pivot function. So here's another interesting point. The Jacobian matrix doesn't necessarily have to be symmetric, and it doesn't necessarily have to be diagonally dominant. If it was diagonally dominant, we wouldn't have to necessarily do pivoting. So it's possible pivoting might be critical, otherwise the Jacobian solving that linear system could break down. So we're going to use Gauss pivot here to get the increment, and then do the increment and test whether or not we've achieved convergence. If we go back up here, it's interesting that the reason this if test is occurring twice is because it's possible that from the very get-go we've found the solution. So it's important to solve the original system just to see if we in fact have found the solution to the problem initially. So if the dot product of the functional evaluation, if it's essentially 0, if you found an x1 through xn that essentially is a root for all of those nonlinear equations, you need to stop immediately. And that's what that if test is doing. Otherwise, we compute the increment by solving the nonlinear system, add it to the current estimate, test whether the 2 norm is small enough, and if not, continue on. So this is example 4.9 if you just scroll up a few more pages. So this would be on pages 165 and 166 of your text. This is just a nice little application of our Newton-Raphson 2 Python module, and I'll demonstrate this in just a second, but I'd just like to go over the approach to solve the problem using the code. Here are clearly three, this is a nonlinear system of three variables x, y, and z. So first thing I want to point out is, yes, these variables are x, y, z. They could have been called x1, x2, and x3, but that shouldn't bother you. Now, the third one actually is linear, but all it takes is one of the equations to be nonlinear for the whole system to be nonlinear. So clearly, it's nonlinear in the y here because you see y squared. It's nonlinear in z here because of ln of z, and it's nonlinear in x because of sine x there. You've got an exponential here, 2 to the y here, and you've got a cubic here, z to the cubed. So those are contributing factors for why this is a nonlinear system. The goal is to use the Python module we just talked about, and you have to have a starting guess. So the starting guess is going to be 1, 1, 1 for x, y, and z. So we'll assume the first position is x, the second position is y, the third position is z. And you can automatically say that, well, we know it doesn't satisfy the third equation because 1 plus 1 plus 1 is 3. 3 minus 5 is not 0. So one might argue, maybe you do a better job of choosing maybe this first one to be a 3. But be that as it may, we'll do what the book does and start with this particular initial guess, and then what we'll look at is just the solution to that is simply calling Newton-Raphson 2. The complexity is simply that you have to be able to build a function now for f now, remember, has 3 equations in it, so you index each equation by a single index like this. F bracket 0 will give you the first one, f bracket 1 will give you the second one, f bracket 2. And then return f means returning each of those values for each row, so it's going to be a vector valued result. You'll get 3 components coming back from this call. And so here is just using NumPy and creating an array for your initial guess, pass that to Newton-Raphson, and then let it compute till the tolerance. In this case, since you didn't specify a tolerance, you know the value is going to be 10 to the minus 9. But of course, the user could have put a value there. And hopefully, this is the solution that we'll see when I run this in just a second. And that's going to be the values of x, y, and z that satisfy that 3x3 nonlinear system of equations. So here is the Python script for the example 4_9.py that was mentioned in the book and that I'm sharing with you on Blackboard. There's nothing fancy about this. Notice that we use the Newton-Raphson 2 module, importing all the functions that are used in there, as well as NumPy, and also importing sine and log. You'll need sine and log from the math library because this nonlinear system uses them. So it is important to understand natural log is log. So that is not a binary log or it's not a base 10 log. Log is the natural log by default. And so here's just coding up the f, starting with our initial guess, and then simple as that. Print what, this is telling the interpreter to please print what is returned by the Newton-Raphson 2. And of course, as we saw earlier, it returns the vector that it converges to. And in this case, 3 space. So just simply running it on my desktop machine right here using Python 3.3. Boom. And you go back to look at the book. This pretty much matches, if we look very carefully here, to what we saw in the book. We're pretty much getting we're pretty much getting exactly what we expected to see from the book. So again, both of these modules are available to use. Very elegant method. Really wonderful way of computing a nonlinear system. So the rest of this lecture is just demonstrating how this could be very important in scientific computing with 2 applications that are based on homework problems in the book, because you'll be doing some other types of applications for homework. But I'm going to go over them from the book just to give you an illustration and then show you the code that uses them. So here's an example of using the Newton-Raphson 2 from structural mechanics. This is problem 16 on page 167 in your text. And the concept here is looking at a cable spanning a particular length. So let's assume the length here between two supports is a length L, and suppose this is the midsection, so that this length is L over 2 and this length is L over 2. And we're trying to connect a cable here between these supports with a certain sag. So S is defined as the length of the cable, and this sag, this distance from the horizontal there across the support down is the sag. And it turns out that the length and the sag are related to the span, and it's given by these equations here. So this is an equation representing the sag, and here's an equation related to h, which is this, the sag is the h and the length is s. It's kind of confusing, isn't it, to have sag called h and length called s. Should be probably the other way around. Sag should be s, but either way, this is fine. But notice it's highly nonlinear. So this uses the hyperbolic sign to describe the length of the cable, and the sag is also involves the hyperbolic cosine. And these other parameters that are needed in terms of the angle involves this omega, or W0 divided by T0, the weight of the cable per unit length. So it takes into account the weight of the cable and the tension. So what the tension value is going to be at this lower point, or the critical point there, 0, at the bottom of the sag. So the idea here is to compute actually what the length of the cable would have to be if the length from the supports, L, is 160 meters and the sag is 15 meters. So it's to compute S given those constraints on L and H. So in solving for this particular length, S, again, you're given L is 160 and H is 15 meters. Now, one might think that, okay, this would involve maybe using our Newton-Raphson 2 module to solve a system of two nonlinear equations. Well, the fact is all you're asked for in this problem is to compute S. So if we can figure out what H is, right, then, well, actually we know what H is. We're given H is 50 meters. What we don't know is lambda. We don't know this lambda parameter. But if we could set this H equal to 15, right, and solve this nonlinear equation here for lambda, then we could plug that in over here and we'd know exactly what the sag was. So here's an illustration of, well, you wouldn't have to necessarily jump to use a nonlinear system. You can actually solve one equation first. And that's exactly the way this problem would be solved, is that we know what H is 15, we know what the L is 160. So the solution in this particular case involves solving this equation here. We're going to write the sag equation in the sense that if we know that left-hand side is 15, then we could solve this in terms of a root finding method. Just say, well, if it's equal to 15, then the 1 over lambda times that hyperbolic cosine component minus 15 has to be equal to 0. And if you were to plot this function, as indicated in this graph, you can sort of figure out an estimate of where the root is. The root is somewhere between 0.004 and 0.005. And so that's exactly how you would set this up. So you could initially define the function in terms of a lambda parameter based on the hyperbolic cosine component, and then this function right here, Ritter, is basically an implementation of the Newton-Raphson method we had before, and the initial guess is going to be 0.0045 with a relatively large tolerance there. We don't need to iterate very long. And so what it actually does is it computes that lambda parameter, and then we can plug that value in to get the length of the cable because we have the cable length function there. And so it would determine that the cable had to be about almost 164 meters for that particular sag. So here's just a very nice illustration of solving one nonlinear system first and then using it to solve the second nonlinear system without having to resort to using Newton-Raphson 2. The other example of solving nonlinear systems is given by problem 26, which is on pages 170 and 171. And I really like this because it's a great illustration of how nonlinear systems arises in computer graphics. And so you should be familiar with the equation of a circle, which is indicated here on the statement of the problem. If you have a center and a radius, a center is AB and the radius is R, this is a description of all the points x, y that satisfy that circle on a two-dimensional Cartesian coordinate system. And so the idea here, again, R is the radius, A and B is the coordinates of the center. Suppose you were given 3 points that should be on the circle. So here's the x, y coordinates that you're hoping will be on the circle. The idea is to figure out, well then, where would the circle have to be centered, and what would be the radius of that circle? So it's sort of giving the constraints of 3 points lying in 2D space. I want a circle that goes through those points. So this is a very interesting way of describing the sort of circle fitting of data, where clearly the equation of a circle is nonlinear because of those squares. So it's definitely not a linear equation. So it's a quadratic equation, and we're having to figure out what the components A, B of the center should be, as well as what the radius is. So the solution of the problem is basically to take each one of those 3 points and use each point to define all the constraints on A and B and R. So for example, here's the first point that we were given involving, again, x and then y was 0. So it's you're just going to plug in the corresponding x coordinate and y coordinate for each of those points, and you will come up with 3 different quadratic equations. In other words, there's squares involving A and B and then R. So your idea is to find the A, B, and R that satisfies those 3 nonlinear equations. Right? So basically, you should be able to it should be a very straightforward application of Newton-Raphson 2. The question mark might be, well, what's a good starting point? What would be a good way of estimating an initial value for the center, the initial coordinates for the center as well as the radius? And one thing could be to, as illustrated here, just if we sort of were looking at those 3 data points that we were given, and again, we're trying to fit a circle. You could imagine drawing a circle that's going to go through those 3 points. You know, you could come up with some reasonable estimates about where the center would be. In this case, we could sort of get a sense that the center might be somewhere in this area, so we could use those coordinates, which would be 5, 3, and the length from the points to that estimated center might be around 5. Again, it's just an estimate. So, so what one would do then to solve the problem is, define the f function, initialize it to zeros, and then in the first row return the value that you would get for plugging in the 3 components. X0 will represent A, X bracket 1 will represent B, and X bracket 2 will represent R, right? And because again we're passing a vector X. Keep in this in mind. I didn't define A, B, and R here. I'm going to use X as an array, and so its first component will basically reflect A, the second component is going to reflect B, and this component reflects R. Might be a good idea to put a comment in this function so that the user of the function would understand that mapping. And then again, here is the second equation being evaluated given the 3 components of A, B, and R, and then the third. Right? And then we have our initial guess to the center, 5, 3, and and our guess for the radius 5, and we're going to pass that into Newton-Raphson in terms of the X array here. We've got our F there, and it basically determines what converges to this value, that the center is really around. We weren't off too bad. The center isn't 5, 3. The center is 4.83 and 3.96, and the radius is not far from 5. It's actually 5.21.